Our solar system is a tiny island in a vast cosmic ocean. For centuries, we thought its orderly arrangement of planets was the standard model for how star systems form. But we were wrong. The discovery of worlds orbiting other stars has completely rewritten the rules of planetary science. These exoplanets reveal a universe far stranger and more diverse than we ever dreamed. You are about to journey through 25 profound mysteries hiding in star systems that look a lot like our own. By the end, you will see our place in the galaxy in a completely new light. We will uncover planets with orbits that defy logic and worlds that are actively evaporating before our eyes. What cosmic secret do you think will be the most shocking to uncover? Our own solar system is a model of celestial order. All 8 planets travel around the Sun in nearly the same flat plane, like runners on a circular track. This predictable alignment is what we long assumed was the norm across the galaxy. But the first profound mystery shatters that assumption. We have found countless worlds that spin backward or travel over the poles of their star, following orbits so wildly tilted they defy every model of planetary birth. Imagine a planet that does not circle its sun like Earth, but instead loops around it vertically in a path that seems to defy gravity itself. These are not rare exceptions. They are shockingly common. This chaotic reality poses a fundamental question. How can a planet form from a spinning, flattened disk of gas and dust, only to end up on a completely different plane or even moving in the opposite direction? One leading theory points to cosmic violence in a system's youth. A close gravitational encounter with another star or a dramatic clash between giant planets could have kicked a world out of its original orbit, sending it tumbling into a new, bizarre trajectory. These gravitational kicks are like cosmic billiard balls, rearranging the entire architecture of a young system. Another possibility involves the star's own magnetic field interacting with the planet-forming disk in complex ways, slowly pushing and pulling worlds into misaligned paths. The implications are staggering. A planet on a severely tilted orbit would experience extreme and erratic seasons. Its climate could swing from scorching heat to deep freeze over the course of a single, long year, creating an environment of relentless turmoil. For any potential life, this would be a constant, brutal challenge. The very existence of these tilted worlds forces us to rewrite the story of how planetary systems are born and evolve. Our solar system, with its calm and orderly dance, now appears to be the true cosmic outlier. This discovery reveals that chaos is not the exception in our universe, but perhaps the rule. Just as we grapple with these chaotic orbits, a second, quieter mystery emerges from the census of alien worlds. Our own solar system presents a clear division. We have the small, rocky inner planets like Earth and Mars, and then the much larger gas and ice giants like Neptune and Jupiter. There is nothing in between. But look out across the galaxy, and this gap is filled to overflowing. The most common planets we find are the so-called super-Earths and mini-Neptunes, worlds that are fundamentally absent from our own cosmic neighborhood. A super-Earth is a planet with up to 10 times the mass of our own, but it is a misleading name. These worlds are not necessarily Earth-like at all. Some might be massive, rocky spheres, true super-sized versions of our home, with crushing gravity and perhaps thick, Venus-like atmospheres. Others, however, are the mini-Neptunes. These are thought to be gaseous worlds, smaller and denser than Neptune, likely composed of a rocky core enveloped by a deep, immense shroud of hydrogen and helium gas. The sheer number of these intermediate-sized planets tells us that our solar system's architecture is not just orderly, but also strangely incomplete. We seem to be missing the most popular model of planet in the cosmos. This leads to an even more specific puzzle known as the radius valley. When astronomers plot the sizes of thousands of exoplanets, they notice a curious gap. There are plenty of planets slightly larger than Earth and plenty that are the size of mini Neptunes, but there is a pronounced dip, a valley, in the number of planets with a radius about 1.8 to 2 times that of Earth. It is as if nature has a preference, skipping over this specific size range. What causes this valley? The leading theory is a dramatic process of atmospheric stripping. A young, warm planet orbiting close to its star might start its life as a mini Neptune with a vast, puffy atmosphere. But over billions of years, the intense radiation from the star could boil away that primordial gas envelope, leaving behind only the bare, rocky core. That core would then appear in our surveys as a super-Earth. The radius valley, therefore, may be the cosmic dividing line between those planets that could hold onto their gas shrouds and those that could not. It is a fossil record of planetary evolution written in the demographics of size. This means that a planet's fate, whether it becomes a water world, a gas-covered orb, or a barren rock, is a delicate balance between its initial formation and the relentless fury of its sun. The radius valley reveals a planet's struggle for survival against its star. But what about worlds that seem to defy survival entirely? Enter the baffling case of the hot Jupiters. These are gas giants, colossal planets like our own Jupiter, but they orbit so close to their suns that a single year lasts only a few Earth days. Imagine a Jupiter-sized world so near to its star that its atmosphere is heated to thousands of degrees, blistering under a perpetual, hellish noon. This existence is a direct contradiction to everything we thought we knew about how gas giants form. These behemoths are born in the cold, outer regions of a protoplanetary disk where ice and gas are plentiful. They simply cannot form in the hot, inner system where only rock and metal can survive. So how did they get there? The leading explanation is one of the most dramatic processes in planetary science: planetary migration. A young gas giant may form in its expected, distant orbit, but gravitational interactions with the leftover gas and dust of the disk or with other planets can act as a brake, causing the world to lose orbital energy. It begins a slow, inexorable spiral inward, marching closer and closer to its stellar parent over millions of years. This migration is a cosmic event that reshapes the entire system. As a hot Jupiter plows inward, its immense gravity acts like a wrecking ball. Smaller, rocky planets in its path are either consumed by the star, flung out into the dark abyss of interstellar space, or shattered into debris. A system that might have once looked familiar with terrestrial worlds in the habitable zone is completely sterilized and rearranged. Our own solar system, with Jupiter remaining peacefully in its outer orbit, appears remarkably calm by comparison. The existence of hot Jupiters tells a story of violent adolescence, where the gravitational ambitions of a single giant planet can dictate the fate of every other world in the family. Hot Jupiters are not the only worlds living on the edge. Far closer in, almost skimming the stellar surface, we find the most extreme survivors of all. These are the ultra-short period planets, entire worlds that complete a full orbit in less than one Earth day. A year for them is a matter of mere hours. The conditions on these blistering worlds are almost beyond comprehension. They are so close to their star that their surfaces are likely vast, global oceans of molten rock, permanent lava worlds glowing with incandescent heat. Others may be the skeletal remains of planets, colossal spheres of solid iron forged in an unimaginable furnace. The very existence of such a planet defies logic. How can anything hold itself together under such an onslaught? The gravitational tide from the star at that proximity is immense, a force that should, in theory, tear a world apart or grind it into dust. Their survival is a testament to incredible density and strength. One compelling theory is that these are the shattered cores of much larger planets. A catastrophic head-on collision between two worlds in the chaotic early days of the system could have stripped away their outer layers of rock and mantle. All that would remain is the dense metallic heart, a planetary core left exposed to the vacuum of space. This iron-rich sphere, now a planet in its own right, would be massive and sturdy enough to resist the star's tidal forces. Another possibility is a unique and final migration path. A planet could have been nudged by gravitational interactions onto a long, elliptical orbit that brought it perilously close to the star on each pass. Over eons, the star's gravity would have circularized that orbit, but also stripped the planet's atmosphere and outer layers, leaving behind only the most resilient materials. These ultra-short period planets are the ultimate endpoint of planetary evolution, the final, dense relics of a system's violent history. They are a stark reminder that a planet's location is not always a gentle cradle, but can be a forge of unimaginable power, reshaping worlds into forms we are only beginning to recognize. The extreme orbits of these scorched worlds reveal a system's violent history, but elsewhere we find evidence of a far more delicate cosmic order. Some star systems are governed by an exquisite gravitational harmony known as orbital resonance. This is not a chaotic free-for-all, but a precise clockwork dance where planets orbit in perfect mathematical ratios. For every 2 orbits one world completes, its neighbor might complete 3 or 4, or another simple integer ratio. Their gravitational tugs become synchronized, creating a stable, repeating pattern that can last for billions of years. It is the universe's own form of music, written in the language of gravity and motion. Our own solar system has minor resonances, like the dance between Pluto and Neptune, but we lack a grand, linked chain of multiple worlds moving in perfect sync. This makes the resonant chains we see around other stars all the more special and mysterious. How does such a fragile, beautiful arrangement come to be? The process begins in the system's infancy within the protoplanetary disk. As young planets form, they naturally migrate inward through the disk, their gravity interacting with the surrounding gas and dust. During this slow drift, they can become captured by each other's gravity, falling into these stable, rhythmic patterns. Once locked in resonance, their orbits are protected. Their periodic gravitational nudges reinforce the stability, preventing them from drifting closer together or colliding. It is a self-correcting system, a celestial feedback loop that maintains order across astonishing spans of time. Yet for all their stability, many of these resonant chains do not last. We find systems with planets that are almost in resonance, their ratios slightly off, hinting at a past harmony that was somehow broken. This disruption points to a turbulent past, a close pass by a wandering star, the gravitational influence of a hidden, distant planet, or the slow, cumulative effects of tidal forces can all provide enough of a nudge to throw the delicate clockwork out of sync. A disrupted resonance is therefore a fossilized clue. It tells astronomers that something momentous happened in that system long after its planets formed. It is evidence of a gravitational shock, a past instability that sent ripples through the cosmic music, leaving the planets in their current, slightly discordant orbits. The search for these resonant chains and their broken remnants allows us to listen in on the gravitational conversations between worlds, hearing both the perfect harmonies and the echoes of ancient disruptions that shaped their fates. Yet, not all giants are dense survivors like these iron relics. Some planets are the exact opposite, celestial phantoms with densities so low they are almost unreal. These are the puffy planets, worlds with the mass of a giant but the density of a marshmallow. Imagine a planet the size of Jupiter but with barely 1% of its mass. A world so bloated and diffused that if you could find an ocean large enough, it would float. Scientists often call them cotton candy planets because their incredibly low density defies our basic understanding of planetary structure. They are not solid spheres of rock and metal, but vast, hot atmospheres held together by a comparatively tiny core. The primary suspect for this extreme puffiness is intense stellar radiation. A planet orbiting very close to a young, active star is bombarded by a flood of ultraviolet and X-ray energy. This incoming radiation heats the planet's outer atmosphere, causing the gases to expand dramatically, like a balloon left in the sun. The planet's own gravity struggles to hold onto this swollen envelope, creating a temporary, inflated state that can last for hundreds of millions of years. But stellar radiation is not the only possible explanation. Some of these worlds might harbor immense internal heat sources left over from their violent formation. This trapped heat could act like an oven, constantly puffing up the atmosphere from within. Another theory suggests their cores are fundamentally different, perhaps composed of unusually light materials or possessing a structure that generates extra heat through tidal friction, where the gravitational pull of the star constantly flexes and stresses the planet's interior. Whatever the cause, these puffy giants represent a fleeting phase in a planet's life. They cannot hold onto their extended atmospheres forever. Over billions of years, the relentless stellar wind may strip the gases away entirely, leaving behind a much smaller, denser core, a ghost of the bloated world it once was. They are a reminder that a planet is not a static sculpture, but a dynamic and evolving entity, capable of existing in forms that challenge our very definition of the word world. While some planets are puffed up by their star's heat, others are actively being torn apart by it. These are the disintegrating worlds, planets caught in the final, violent act of their life cycle. We detect them not by the solid shadow of a planet, but by a strange, shimmering dip in starlight. The light from their star does not dim cleanly and then recover. Instead, it flickers and fades in an uneven, messy way, as if something is blocking the light in a diffuse, shifting cloud. That something is the planet itself, or rather, what is left of it. These worlds are believed to be evaporating, their surfaces heated to such extreme temperatures that rock and metal are vaporizing, creating a colossal plume of dust and gas that trails behind the planet like the tail of a comet. This tail can be many times larger than the planet itself, a ghostly shroud that betrays its ongoing destruction. What could cause such a dramatic end? The primary culprit is relentless stellar radiation. A planet orbiting incredibly close to a ferociously active star is subjected to a continuous blast of energy. This is not the gentle warmth we receive from the sun, but a stellar hurricane that literally cooks the planet's surface, peeling it away layer by layer. The planet's own gravity is too weak to hold onto this superheated material, and so it escapes, forming that vast, disintegrating tail. Another, more sudden cause could be a catastrophic collision. A high-speed impact with another large body, like an asteroid or even another planet, could have shattered the world, leaving behind a cloud of debris that continues to orbit the star, slowly spreading out and fading. The ultimate fate of such a world is a grim one. It will continue to lose mass, shrinking over millions of years until only a dense, barren core remains, or perhaps it vanishes completely, its material scattered into the void or accreted by its star. These dying planets offer us a rare and sobering glimpse into the final stages of planetary evolution. They are a stark reminder that a world is not a permanent fixture. It can be a transient structure in the cosmos, its existence a delicate balance between the forces of gravity and the relentless power of its sun. The slow, agonizing death of a disintegrating planet shows one extreme of stellar influence, but there is another, stranger fate that awaits many worlds in the habitable zone. Billions of planets are likely tidally locked to their stars, forever showing one face to the light and the other to the endless dark. This creates a world of permanent contrast, a global environment of such radical extremes it challenges our very definition of habitability. On the star-facing side, a searing, perpetual day, the ground bakes under an unrelenting sun with temperatures so high that lead would flow like water. On the opposite hemisphere, a frozen, eternal night where the atmosphere itself might collapse into snow onto a glacier-covered landscape. Yet between these two inhospitable realms, there could exist a fragile sliver of possibility. This is the concept of the eyeball planet. Imagine a world with a vast, stagnant ocean on its day side. The relentless stellar heat would keep a central region of this ocean liquid, a single, circular sea of open water resembling the dark pupil of a giant eye staring into space. Surrounding this liquid pupil would be a ring of ice, a frozen iris that gradually thickens as you move toward the terminator, the line separating day from night. Beyond that line, the entire night side would be encased in a global ice cap, a continent-sized glacier under a sky of permanent stars. The climate of such a world would be utterly alien. There would be no day-night cycle, no sunrise or sunset. Weather patterns would be locked in place, driven not by the rotation of the planet, but by the immense temperature difference between the two hemispheres. Fierce, permanent winds could howl from the hot day side to the cold night side, while the ocean currents would be a slow, global conveyor belt, carrying warmth from the day side to the edge of the night and cold back again. Could life emerge in the liquid pupil of an eyeball world? The constant energy from the star would provide a steady source of light for any potential photosynthesis, but the stability of the environment is a double-edged sword. Evolution thrives on change and challenge, and a climate that is literally frozen in time might struggle to foster the dynamism that drove life's great innovations on Earth. Any life forms would be confined to that narrow, temperate ring, trapped between a scorching desert and an abyssal freeze. They might never even know that the other half of their world exists, their entire universe defined by the slow churn of a single, giant sea under a sun that never moves. The existence of these worlds forces us to expand our imagination. A habitable zone is not simply a region where liquid water can exist. It is a place where a planet's geology, its rotation, and its atmosphere must all conspire to create a balance delicate enough for life to take hold, yet robust enough to survive the strange and static realities of cosmic motion. Even the death of a star is not the end of the story for the worlds that once orbited it. Around the faint, cooling embers known as white dwarfs, astronomers have uncovered a ghostly signature of destruction. The pristine atmospheres of these dead stars, which should be composed almost entirely of the lightest elements, hydrogen and helium, are instead mysteriously polluted. They are contaminated with heavy elements like iron, silicon, and calcium, the very stuff of rock and metal. This is a cosmic crime scene, and the evidence points to a gruesome fate for the star's former planetary system. A white dwarf possesses such immense gravity that any heavy elements in its atmosphere should sink almost instantly into its core, leaving its surface pure. The fact that we see these pollutants at all means they are being actively and continuously fed onto the star. The only plausible source is the shredded remains of asteroids, moons, and even entire planets that wandered too close. Long after the star's death, its gravitational reach remains a destructive force. This pollution reveals a dramatic sequence of events. When a star like our Sun dies, it bloats into a red giant, incinerating and engulfing its inner planets. But the outer worlds and the vast asteroid belts would survive, pushed into wider, more unstable orbits by the star's mass loss. In the ensuing gravitational chaos, these surviving objects can be perturbed, their paths altered until they fall inward toward the white dwarf. The star's immense tidal forces then take over, stretching and compressing any sizable object until it is ripped apart into a cloud of dust and debris. This cloud forms a glowing, thin disk of rubble, a final monument to the destroyed world, which slowly spirals down to pollute the white dwarf's surface. This process tells us that planetary systems are not necessarily stable forever. They can undergo violent rearrangements billions of years after their star has died. The ultimate fate of our own solar system may be written in these polluted stars. Billions of years from now, when our Sun becomes a white dwarf, the asteroids of the main belt, the moons of Jupiter, and perhaps even the inner planets themselves, could be gravitationally tossed into a deadly dance, destined to be torn apart and accreted onto the stellar corpse that was once their sun. The polluted atmospheres of white dwarfs are therefore more than just celestial curiosities. They are tombstones recording the final dissolution of entire families of worlds. Far from the warmth of any star, a deeper darkness moves between the stars. These are the rogue planets, entire worlds untethered from any solar system, drifting alone through the galactic void. Detecting these solitary wanderers is one of astronomy's greatest challenges, as they emit no light of their own. We find them only when they pass directly in front of a distant background star. For a fleeting moment, their gravity acts as a lens, bending and magnifying the starlight in a telltale brightening known as microlensing. It is a ghostly signature of a passing shadow. The existence of these worlds presents a profound mystery of origin. Were they born in the chaos of a young star system, only to be violently ejected by gravitational encounters with sibling planets? Or could some of them have formed in total isolation, coalescing from tiny, cold clouds of gas and dust too small to ever ignite into a star? The evidence points to ejection as a primary cause. In the unstable youth of many systems, the gravitational dance of giant planets can fling smaller worlds out into the abyss, casting them adrift on an eternal journey. The conditions on such a world are the definition of extreme. With no sun, the surface temperature would hover just a few degrees above absolute zero, a perpetual and deep frozen night where any atmosphere would collapse into a blanket of ice. Yet within this frozen shell, a tantalizing possibility remains. Many of these rogue planets, especially larger ones similar to Jupiter or Neptune, could retain immense heat from their formation, trapped deep within their cores. This internal furnace, possibly supplemented by the radioactive decay of heavy elements, might be enough to maintain vast global oceans of liquid water beneath a thick, icy crust. Imagine a world with a surface harder than granite, where the sky is a permanent canvas of stars without a sun, but hidden below lies a dark, abyssal sea warmed from within. The potential for life in such an environment, while slim, cannot be entirely dismissed. We know that on Earth, entire ecosystems thrive around hydrothermal vents on the dark ocean floor, completely independent of sunlight. A rogue planet's subsurface ocean could, in theory, host similar chemosynthetic life, drawing energy from the planet's internal heat and the chemistry of the seafloor. These dark, wandering worlds challenge our most basic assumptions about what makes a planet. They may be among the most common objects in our galaxy, a vast, unseen population of nomads carrying within them the faint, frozen ember of possibility, even in the absolute cold of interstellar space. The lonely drift of rogue planets stands in stark contrast to the complex choreography found in binary star systems. Here, a planet does not orbit a single sun but two. These are the circumbinary planets, real-world versions of the fictional Tatooine, and their very existence is a triumph of celestial stability. Picture the dynamic challenge. Instead of a single, steady gravitational pull, a planet here is constantly tugged by two different stars, which are themselves whirling around each other in a tight dance. This creates a gravitational landscape that is perpetually shifting and uneven. For a planet to survive here, it must find a very specific path, a wide orbit that circles both stars far outside their own chaotic waltz. If it ventures too close, the competing gravitational forces would stretch and pull the world until it was torn apart or flung out of the system entirely. Finding this stable zone is like finding the single, calm spot in the center of a spinning vortex. The light these worlds receive is equally chaotic. Their years are not consistent. Depending on the star's positions, the planet might bask in the light of two suns, casting double shadows, or it might experience a solitary day under just one. The sunsets would be a spectacle beyond anything on Earth, As the planet rotates, one star might dip below the horizon, followed sometime later by the second, creating a prolonged double twilight. At other times, the two stars could eclipse each other from the planet's perspective, causing sudden, dramatic dips in brightness. The resilience of these worlds forces us to reconsider the planet formation process. They prove that planets can coalesce from a disk of gas and dust even in the tumultuous environment of a binary system. The primordial disk must have been strong and stable enough to withstand the gravitational tides of two young stars, allowing planetary building blocks to clump together far from the central chaos. The discovery of these systems tells us that planet formation is not a delicate process confined to serene, single-star nurseries. It is a robust, almost stubborn force of nature, capable of building entire worlds in some of the most dynamically violent neighborhoods in the galaxy. The very elements that forged our solar system may be its most decisive ingredient. We are all quite literally made of stardust, the remnants of long-dead stars that exploded and seeded the cosmos with heavy elements. This cosmic inheritance, known as a star's metallicity, holds a puzzling key to the planets that form around it. Astronomers have uncovered a strange and powerful correlation. Giant Jupiter-like gas planets show a strong preference for stars rich in metals. In contrast, smaller, rocky worlds like Earth are found around stars of all metallicities, from the metal-rich to the metal-poor. This pattern strikes at the heart of how we believe planets are born. The leading theory, called core accretion, suggests that planets form from the bottom up. First, dust grains in the protoplanetary disk collide and stick together, building ever larger bodies. For a gas giant to form, this process must happen incredibly fast. A massive, rocky core, perhaps 10 to 15 times the mass of Earth, must assemble before the young star's radiation blows away the primordial hydrogen and helium gas from the disk. This is where metallicity becomes crucial. A disk surrounding a metal-rich star is essentially pre-loaded with more of the dust, rock, and ice particles that are the building blocks of planetary cores. In this dusty environment, those initial clumps can form more easily and grow much faster, racing to build a core massive enough to begin rapidly pulling in the vast shroud of gas that makes a giant planet. Around a metal-poor star, the disk is cleaner with far less solid material. The growth of planetary cores is a slower, more difficult process, and the window of opportunity to capture a giant atmosphere often closes before a large enough core can form. The result is a system dominated by smaller, rocky worlds. This leads to a profound question about our own existence. Our Sun is a fairly metal-rich star, and it hosts one gas giant, Jupiter. Was our Sun's specific metallicity the golden ticket that allowed Jupiter to form, a cosmic event that may have been essential for life on Earth? Jupiter's immense gravity is thought to have acted as a protective shield in the early solar system, deflecting and absorbing countless comets and asteroids that might have otherwise pummeled the inner planets into sterility. Without that specific metallicity, would Jupiter have never coalesced? Would Earth have been bombarded into a lifeless state or never formed at all? The mystery of stellar metallicity suggests that the recipe for a solar system like ours is not just about the right amount of stardust, but the precise timing and abundance of it, a delicate balance that may make complex life far rarer in the cosmos than we ever imagined. The dust from a star's violent birth never truly settles. Long after the planets have formed, vast clouds of leftover debris continue to orbit, the celestial equivalent of a construction site after the builders have gone home. These are the debris disks, and their intricate structures hold secrets far beyond simple rubble. Our own solar system has two such rings, the asteroid belt and the distant Kuiper belt. But around other stars, these disks are not the smooth, uniform halos we might expect. They are riddled with sharp edges, strange gaps, and dramatic warps, as if sculpted by an invisible hand. These are not chaotic accidents. They are forensic blueprints etched in dust that point directly to the presence of hidden worlds. A gap in a debris disk is a powerful clue. Imagine a vast field of orbiting rocks and ice. If an unseen planet is circling within that field, its gravity acts like a cosmic shepherd. It clears its own orbital path, pushing and pulling smaller objects away over millions of years. The result is a clean, dark band within the bright disk, a silent testimony to a planet we cannot yet see directly. The sharp, defined inner edge of our own Kuiper belt, for instance, is strongly suspected to be the work of Neptune's gravity, a boundary it shepherds and maintains. But the mysteries go deeper than simple gaps. Some debris disks are not flat, symmetrical platters at all. They are warped, tilted, or bent into shapes that defy a simple, quiet history. A massive planet orbiting on a tilted plane would exert a persistent gravitational pull on the disk, torquing and twisting it over eons, forcing the entire cloud of debris to precess or wobble like a slow-motion spinning top. Other disks show clumps and arcs, dense concentrations of material that should naturally spread out over time. These too are the scars of gravitational encounters, perhaps with a planet on a very elongated orbit that periodically stirs the debris like a stone thrown into a pond, creating ripples that never fully settle. Every sharp edge, every warp, every gap is a chapter in that system's history book. By reading these patterns, astronomers can deduce not just the presence of a hidden planet, but often its approximate mass and its orbital path, all from the subtle influence it has on the dust left over from its own birth. These disks are more than just leftovers. They are dynamic, living environments, constantly reshaped by the very planets they help to create, offering us a powerful new way to map the hidden architecture of entire solar systems. A star's death is not always the end for its planetary family. Some worlds possess a resilience that borders on the impossible, enduring an apocalypse that should have vaporized them entirely. When a star like our Sun exhausts its nuclear fuel, its final act is one of cosmic violence. It swells into a red giant, a bloated inferno that expands to engulf the orbits of its innermost worlds. Mercury, Venus, and likely Earth would be swallowed whole, scorched into nothingness. Yet, against all odds, astronomers have found evidence of planets that survived this very fate. These are the cosmic survivors orbiting the stellar corpses left behind, the white dwarfs and neutron stars. How can a planet live through such a cataclysm? The key lies in distance and a star's surprisingly gentle demise. While the red giant phase is destructive, the star loses a tremendous amount of its mass in the process. It sheds its outer layers into a beautiful planetary nebula, and its core collapses into an ultra-dense white dwarf. This mass loss dramatically weakens the star's gravitational grip. Worlds that were once in stable, distant orbits suddenly find themselves in a much roomier system. Their orbits expand like a tetherball on a suddenly lengthened rope, potentially moving them just far enough away to avoid the expanding stellar fire. A planet that was once where Jupiter is in our system could be pushed out to the distance of Saturn, placing it in a new position to witness its star's death. The resulting system is a ghost of its former self. A solitary, scorched giant planet or a collection of asteroids might now circle the tiny, hot ember of the white dwarf. The conditions on these survivor worlds are mind-bending. They are bathed in an eerie, perpetual glow. A white dwarf emits a fierce, ultraviolet rich light, while a neutron star pumps out deadly X-rays and particle winds. Any atmosphere would be swiftly stripped away by this relentless radiation, leaving behind a barren, irradiated rock. The sky would be dominated by the tiny, brilliant point of the stellar corpse, casting sharp, black shadows across a landscape that had been baked and scoured clean. The very concept of time is warped near a neutron star. The immense gravity of such an object causes time dilation, an effect predicted by Einstein. A single orbit for one of these planets might take only a few hours, but for an outside observer, time on the world's surface would appear to crawl. A clock on the planet would tick significantly slower than a clock in the rest of the galaxy. These post-apocalyptic systems are the ultimate test of a planet's endurance. They show us that a world can persist through the most extreme events, but the price is a transformation into something utterly alien, a silent memorial to a stellar life that once was. These alien atmospheres are laboratories of the impossible, where the very air is a chemical marvel. The diversity we have found is staggering, with exotic compounds and weather patterns that defy any Earth-based logic. Imagine a world where the daytime sky is a perpetual, hazy twilight, not from water clouds but from a vaporized metal like titanium oxide. This substance, a common ingredient in sunscreen, can exist as a gas in the intense heat of some exoplanet atmospheres, actively absorbing light and creating a powerful thermal inversion, a layer where temperature increases with altitude instead of decreasing. This creates a global heat trap, turning the entire planet into a blistering, stratified oven. On other worlds, the conditions are right for clouds to form not from water but from silicates. When temperatures soar high enough, rock itself can evaporate, rise into the atmosphere, and then condense into droplets of liquid rock or tiny grains of sand. This leads to a truly surreal meteorological phenomenon, a steady rain of molten glass falling through skies of vaporized stone. How can we possibly know what the air is like on a world light years away? The primary technique is transit spectroscopy. When a planet passes in front of its star, a tiny fraction of the starlight filters through the planet's thin atmospheric rim. Different gases in this atmospheric ring absorb specific colors of this light. By analyzing which colors are missing from the starlight that reaches us, astronomers can decode the chemical fingerprint of the atmosphere itself. It is like identifying the ingredients in a distant soup by studying the precise shade of light shining through its steam. But this data is incredibly faint and difficult to interpret. A single measurement is just one piece of a vast three-dimensional puzzle. The atmosphere has different layers, various cloud types, and global circulation patterns that all mix the signal together. A detection of water vapor, for instance, could mean a humid, tropical world, or it could be from a high, cold layer of a mostly dry planet. This is the great challenge, separating the true nature of the world from the ambiguous whispers of its light. These alien skies are more than just chemical curiosities. They are dynamic records of a planet's deepest nature. The presence of certain gases can reveal a world's volcanic activity, the composition of its surface, and the ferocity of its weather. Storms on a gas giant with supersonic winds would churn the atmosphere, dredging up material from deep below that we can then detect. And for the holy grail of this search, the potential biosignatures, the atmosphere is the only canvas upon which life can paint a detectable signature. On Earth, the simultaneous presence of large amounts of oxygen and methane in our air is a powerful clue to life, as these gases react quickly and would vanish without constant biological replenishment. Finding a similar, unstable chemical cocktail on a rocky world in the habitable zone would be our strongest hint that we are not alone. Each strange atmosphere, with its titanium haze and glass showers, forces us to expand our understanding of what a planet can be, pushing the boundaries of chemistry, geology, and our own imagination. Finding a planet within the habitable zone feels like a monumental discovery, a world where liquid water could theoretically exist on the surface. But this zone is not a guarantee of life. It is merely the starting line in a cosmic marathon of habitability. The simplistic idea of a Goldilocks zone crumbles under the weight of countless other factors that can render a world a scorching desert or a frozen tomb. A planet's true potential for life is a fragile balance dictated by forces both seen and unseen. One of the most powerful hidden engines is tidal heating. A planet does not need to be close to its star to be warm. If it orbits a gas giant or is locked in a gravitational dance with sibling moons, the constant stretching and squeezing from these tidal forces can generate immense internal heat. This is the same process that keeps the interior of Jupiter's moon Io a molten inferno, driving the most volcanically active world in our solar system. A rocky planet with significant tidal heating could maintain a subsurface ocean for billions of years, even while drifting far outside the traditional habitable zone. Its warmth would come not from a sun, but from the gravitational friction of its own orbit. Yet, even with ample heat and water, a world remains defenseless without a planetary magnetic field. This invisible shield is generated by a churning, molten metal core, a planetary dynamo that deflects the relentless onslaught of stellar radiation and charged particles. Without this protection, a star's solar wind would slowly but surely strip away the planet's atmosphere, evaporating its oceans and scouring its surface sterile. Mars serves as a solemn reminder, a world that likely once had flowing water but lost its magnetic field, leading to its atmosphere being torn away by the solar wind over eons. The nature of the star itself is another critical variable. A planet might orbit perfectly within the habitable zone of a red dwarf star, but these stars are often tempestuous and prone to violent flares. A single, massive stellar eruption could bathe a nearby world in enough ultraviolet and X-ray radiation to sterilize its surface and obliterate any potential ozone layer. A planet's atmosphere is its final and most complex line of defense. Its composition acts as a global thermostat. A thick carbon dioxide atmosphere could create a runaway greenhouse effect, turning a world into a hellscape like Venus. Too thin an atmosphere and the planet cannot retain enough heat, freezing any water solid. The presence of certain gases like methane or oxygen could be a signature of life, but could also be explained by geological processes alone. So when we announce the discovery of another Earth-sized world in the habitable zone, we are not finding a second Earth. We are finding a candidate, a single point of data in a vast equation of stability. We have merely confirmed its address is in the right neighborhood. The real mystery is what happens inside that world, around that world, and above it, a symphony of geological, chemical, and stellar factors that must all play in perfect harmony to turn a merely habitable zone planet into a living world. This grand shuffling of planetary decks is orchestrated by the very material from which planets are born. Within the swirling protoplanetary disk of gas and dust, two powerful migration mechanisms act like cosmic conveyor belts. The first, known as Type 1 migration, affects smaller, Earth-sized worlds. These planets are not massive enough to clear a full gap in the disk. Instead, their gravity creates spiral waves in the surrounding gas. The interplay between the planet's pull and the wave's push creates a net force that can either drag the world inward toward the star or push it outward, all over the course of just a few 100,000 years. It is a subtle but relentless drift, a gentle current that can move entire worlds across a solar system. For larger, Jupiter-sized giants, a more dramatic process takes over. Type 2 migration occurs when a planet grows so massive that its gravity carves a clean, deep trench in the protoplanetary disk. The planet becomes locked within this gap, and its fate is tied to the disk's own evolution. As the entire disk of gas spirals slowly inward due to viscosity, the giant planet is carried along with it like a leaf caught in a draining whirlpool. This process can march a gas giant from the cold outer, reaches all the way into a blistering close orbit, creating the hot Jupiters we observe. The evidence for this grand shuffling is written into the very structure of planetary systems. The empty spaces and peculiar orbital arrangements we see are often the scars of past migrations, and our own solar system may hold its own fossilized evidence of this process. The Grand Tack hypothesis suggests that Jupiter itself was not born in its current orbit. According to this model, Jupiter formed first, much closer to the Sun than it is today. As it grew, it began to migrate inward, a movement that would have scattered the primordial asteroid belt and threatened the formation of the inner rocky planets. But then, the gravitational influence of the newly forming Saturn pulled Jupiter back, causing it to reverse its course and migrate outward to its present position. This gravitational dance, a celestial do between the two giants, cleared the inner solar system of debris and created the conditions that allowed Earth to form and flourish. This idea transforms our solar system from a static monument into a dynamic story of movement and gravitational rescue. The enigma of planetary migration reveals that a planet's current address is often just a temporary stop on a long and winding journey, a journey that can either create the perfect conditions for life or utterly sterilize a system in its celestial wake. The hunt for alien worlds now extends to their silent companions. The riddle of exomoons represents one of astronomy's most daunting frontiers, a search for a tiny speck of light orbiting a distant dot of light, all from thousands of light years away. Detecting a planet is difficult enough, but finding a moon requires witnessing the most subtle of gravitational whispers. The primary method involves looking for a second, smaller dip in starlight just before or after the planet's own transit, or for tiny variations in the exact timing of the planet's orbit caused by the moon's gentle tug. The signals are incredibly faint, buried in stellar noise, pushing our telescopes and algorithms to their absolute limits. Yet, amidst the uncertainty, there have been tantalizing hints. A few candidate systems have shown data that is difficult to explain without the presence of a large Neptune-sized moon, a colossal companion that defies anything in our own solar system. These potential discoveries ignite a profound mystery. Is the process of moon formation a universal rule or a cosmic accident? In our system, moons are created through colossal impacts like the one that gave Earth its moon, or are captured from swirling disks of debris around giant planets. Do these same blueprints hold true across the galaxy? The answer could redefine the very canvas for life. Imagine a gas giant parked comfortably within its star's habitable zone. While the planet itself is a swirling ball of gas, a large, rocky moon orbiting it could possess all the ingredients for life. This would be a true forest moon, a world with a stable climate, liquid water on its surface, and a sky dominated by the colossal, banded sphere of its parent planet. Alternatively, a moon heated internally by the tidal forces of its giant planet could host a global, subsurface ocean beneath a thick shell of ice. An ocean moon where life might thrive in eternal darkness around hydrothermal vents completely independent of starlight. The discovery of just one such habitable exomoon would effectively double the real estate for life in the cosmos. It would tell us that life is not confined to planets orbiting stars, but could flourish in the shadow of giants in the most unexpected of cradles. Finding these hidden companions is more than a technical achievement. It is a search for a second genesis of life, one that could be happening right next door on a world we have only just begun to dream of. The orderly spin of our own sun, its equator neatly aligned with the planet's orbits, is another cosmic convention that appears to be the exception. We now know that the stars themselves can be wildly tilted relative to their planetary families. A star's equator might point in one direction while its planets circle around its poles, a profound misalignment that speaks to a chaotic past. Astronomers measure this cosmic slant using a subtle effect known as the Rossiter-McLaughlin effect. As a planet transits across the face of its rotating star, it sequentially blocks light from the part of the star that is turning toward us and then the part turning away. This creates a distinct, skewed signature in the star's spectral lines, a fingerprint that reveals the precise angle between the star's spin and the planet's orbit. This data paints a surprising picture with a significant number of systems, especially those hosting hot Jupiters, showing severe spin-orbit misalignments. How does an entire system become so tilted? The evidence points toward gravitational upheavals in its infancy. A close gravitational encounter with another star in a dense stellar nursery could have yanked the entire planetary disk and the planets within it into a new orientation, leaving the star spinning in its original direction. Alternatively, the star itself could have been torqued by interactions with a massive, undiscovered companion star orbiting far out in the darkness. Another possibility lies in the internal dynamics of the star. A shifting of mass deep within its interior, or a powerful magnetic field interacting with the planet-forming disk, could have gradually realigned the star's spin axis over millions of years. This widespread misalignment forces a fundamental reconsideration of planetary system formation. It suggests that the calm, flat disk from which planets are born is often just the opening scene. The subsequent chapters are frequently written by gravitational chaos, where stellar flybys and hidden companions act as invisible hands, twisting entire systems into configurations we once thought were impossible. The hunt for unseen planets pushes beyond the cold wanderers we have already discovered. It probes the very edges of known physics into the realm of one of cosmology's greatest enigmas. What if some of the mysterious gravitational lenses we detect are not planets at all, but something far stranger? This is the speculative frontier of dark matter planets. Imagine an object with the mass of a world, perhaps even a giant like Jupiter, but composed entirely of exotic matter that does not emit, absorb, or reflect light. It would be a perfect phantom, detectable only by the way its immense gravity warps the fabric of space-time, bending the light from a distant star behind it in a fleeting microlensing event. We would see the star brighten and fade, a ghostly signature with no visible cause. The nature of such an object defies our everyday experience. A dark matter planet would not have a solid surface of rock or a swirling atmosphere of gas. It would be a dense, diffuse cloud of particles that barely interact with each other or with the normal matter that makes up our world. You could fly a spaceship right through its heart, and aside from a slight gravitational tug, you might not even know it was there. It would be a gravitational presence without physical substance, a shadow in the force of gravity itself. The idea remains highly theoretical, a tantalizing what-if. Most scientists believe the microlensing events we observe are far more likely caused by conventional rogue planets or faint, failed stars. But the mere possibility forces a profound question. Could dark matter, which makes up most of the mass in the universe, ever clump together to form structures as small as a planet? Our current models suggest dark matter forms vast, diffuse halos around galaxies, not compact spheres. Yet the universe has surprised us before. This speculation highlights a deeper truth about the search for exoplanets. It is no longer just a branch of astronomy. It has become a fundamental probe of physics, a way to test our understanding of matter, gravity, and the very composition of reality. Every strange wobble of a star, every unexplained flicker of light, could be a clue pointing toward a new law of nature hidden in the dark spaces between the stars. A planet's magnetic field is an invisible fortress, a shield generated by the churning of its molten core. This dynamo effect creates a vast protective bubble called a magnetosphere, deflecting the relentless supersonic stream of charged particles flowing from its star. Without this shield, a world's atmosphere is left utterly defenseless. The solar wind would slowly but surely strip it away, molecule by molecule, evaporating oceans and scouring the surface sterile over billions of years. We see this tragic fate written on Mars, a world that likely once had flowing water but lost its global magnetic field, leading to its atmosphere being torn away into the void. For any world hoping to nurture life, a robust magnetic field is not a luxury. It is a fundamental requirement for long-term survival. Yet detecting this invisible force on a planet light years away presents one of astronomy's greatest technical challenges. How can we possibly sense a magnetic field we cannot see? The most promising method involves searching for a very specific kind of aurora. When a planet with a magnetic field orbits close to its star, the stellar wind can interact with the magnetosphere, funneling charged particles toward the poles and causing the atmosphere to glow in radio wavelengths. Astronomers listen for these faint radio whispers, a signature of a planetary magnetic field interacting with its sun. Another technique looks for the subtle signs of a bow shock. As a planet moves through the stellar wind, its magnetosphere can plow through this material like a ship's prow cutting through water, creating a detectable shock wave in the star's own emission. Finding the first confirmed magnetosphere around a distant rocky world would be a landmark discovery. It would immediately elevate that planet on the list of potentially habitable worlds, transforming it from a mere candidate into a place that actively protects the delicate conditions life would need to arise and thrive. The conundrum is that we do not yet know how common these planetary shields are. Is Earth's dynamic core a cosmic rarity, or is it the standard for rocky worlds in the habitable zone? The answer will tell us if most planets are like Mars, quietly bleeding their atmospheres into space, or if they are like Earth, guarded by an invisible, energetic force field that keeps their life-giving air securely in place. The birth of a planetary system is a fleeting event in the life of a star, a window of creation that slams shut in just a few million years. Within the swirling, luminous disks of gas and dust surrounding infant stars, we are now witnessing this very process in real time. These are not the quiet, mature systems we have explored so far, but cosmic nurseries where planets are actively being assembled before our eyes. The most direct evidence comes from stunning images of these protoplanetary disks, which are not smooth and featureless. Instead, they are etched with intricate patterns of bright rings and dark, empty gaps, like the grooves on a giant, spinning record. These gaps are the calling cards of newborn planets. As a young world gathers mass, its gravity acts as a cosmic plow, clearing its orbital path of dust and gas. The material piles up at the edges of this cleared zone, creating those bright, dense rings we can observe. We are essentially seeing the construction sites of entire solar systems. This rapid formation poses a fundamental puzzle. How do planets build themselves so quickly from microscopic dust grains? The process begins with gentle collisions. In the calm, outer regions of the disk, tiny particles of ice and dust gently stick together, forming fluffy aggregates that grow into pebble-sized objects. But then, the process must accelerate dramatically. These pebbles are thought to be swept up by larger planetary embryos through a mechanism called pebble accretion. As these embryos orbit, they create a gravitational wake that focuses a stream of pebbles directly into their path, allowing them to grow to the size of a planetary core with astonishing speed. This solves the mystery of how giant planets can form before the star's radiation blows the primordial gas disk away. They must race to build a core massive enough to pull in a vast atmosphere of hydrogen and helium, a process that seems to require this rapid, efficient pebble delivery system. Yet, even as they form, these infant worlds are not stationary. They are born into a dynamic, flowing river of material, and they immediately begin to swim. The young planet's gravity interacts with the surrounding disk, creating spiral waves. The gravitational tug of war between the planet and these waves transfers energy, causing the planet to migrate from its birthplace. It can spiral inward, marching toward the star, or in some cases be pushed further out. This means a planet's current location may have little to do with where it was originally assembled. The entire architecture of a young system is in constant, fluid motion, a grand shuffling of worlds that occurs in mere cosmic moments. Observing these youthful systems is like watching a time-lapse of our own solar system's deepest past, revealing the violent and dynamic birth that sets the stage for everything that follows. Saturn's magnificent rings define our image of a ringed world, but they may be a quiet whisper in a cosmic chorus of extraordinary structures. The riddle of planetary rings extends far beyond our solar system, into star systems where the possibilities become almost unimaginable. While we have not yet confirmed rings around an exoplanet, the methods to find them are taking shape. One approach involves scrutinizing the transit of a planet across its star with incredible precision. If the world has rings, the starlight would dim slightly just before the main transit begins and linger just after it ends, as the rings themselves begin and finish their passage. The light curve would not be a clean, U-shaped dip, but a complex signal with subtle shoulders and asymmetries. Another method relies on the way light scatters. Rings are made of countless tiny particles, and they scatter starlight in a unique way, potentially creating a detectable polarization signature that differs from that of a solid sphere. Finding these signals is like trying to hear a single soft note in a roaring symphony, but the potential discovery would be worth the effort. Imagine rings that dwarf Saturn's, a disk of debris stretching millions of miles from its planet, so vast it would cast a deep, star-spanning shadow. These super rings could exist around a giant planet orbiting far from its star, in a region where tidal forces are weak and the ring material can spread out into a colossal, fragile disk. The composition of these rings might also defy our experience. While Saturn's rings are mostly water ice, an exoring around a scorching hot planet could be composed of silicate dust or even vaporized metals, creating a shimmering, incandescent band of liquid rock and smoke. The very presence of a ring system is a profound clue to the hidden activity in that planetary system. Rings are not permanent, they dissipate over time, spreading out or collapsing onto the planet. For a ring to exist, it must be constantly replenished. The most likely source is a moon or many moons orbiting within the system. A ring acts as a living record of collisions and disruptions. A recent, violent impact between two moons could have shattered one into a billion glittering fragments, instantly creating a new ring. Alternatively, a moon that wanders too close to its planet can be torn apart by tidal forces, its remains stretched into a graceful arc of debris. The intricate structure of rings, with their gaps and braids, often points to the gravitational influence of shepherd moons, small satellites that orbit within the ring system, using their gravity to sculpt the dust and ice into sharp edges and resonant patterns. So the search for exorings is about more than just finding beautiful structures. It is a search for the unseen moons that must accompany them, and for the history of catastrophic moon-making and moon-breaking events that have shaped that distant system. A single, strange dip in starlight could tell a story of a celestial demolition, a cosmic rearrangement that happened just yesterday on the scale of the universe. The silent, drifting debris of a planetary system's youth does not always stay confined to its stellar parent. Our own solar system has recently been visited by strangers from the deep, the first confirmed interstellar objects to pass through our neighborhood. The elongated, tumbling rock named Oumuamua and the familiar icy comet 2I/Borisov are more than just celestial curiosities. They are messengers, and their very existence speaks to a hidden, chaotic reality of cosmic construction. The profound mystery is not just where they came from, but what their presence implies about the galaxy as a whole. The most compelling explanation is that these objects were violently ejected from their home star systems during the chaotic planetary formation process. In the gravitational turmoil of a system's youth, as giant planets jostle for position, they can act like cosmic slingshots, flinging smaller asteroids and comets out into the void at incredible speeds. These objects then become interstellar nomads, destined to wander between the stars for millions or even billions of years. The properties of these visitors are equally telling. Oumuamua's unusual shape and lack of a visible cometary coma puzzled scientists, suggesting it could be a shard of a planet shattered by a catastrophic impact, or a dense, rocky fragment stripped of its volatile ices after eons of exposure to cosmic radiation. In contrast, Borisov looked and behaved much like a comet from our own Oort cloud, indicating that the basic ingredients for icy planetesimals are universal. The sheer number of these objects we are beginning to detect suggests a staggering population of free-floating debris. Current estimates indicate there could be trillions of such interstellar objects drifting through the galaxy, outnumbering stars by a factor of quadrillions. This invisible, drifting mass is the discarded lumber and leftover bricks from billions of years of cosmic construction. Every interstellar passerby is a piece of forensic evidence. By studying their composition and trajectories, we can indirectly sample the building blocks of distant, unknown planetary systems. They tell us that the process of planet formation is inherently messy and violent, a game of gravitational pinball that inevitably flings a tremendous amount of material into the dark. This constant exchange of matter between star systems raises a fascinating possibility. Could the raw ingredients for life, the organic molecules, and perhaps even the precursors to biology, be hitchhiking across the galaxy on these dark, frozen travelers? The interstellar object is a silent testament to a simple, profound truth. No solar system is an island. They are all connected by this faint, steady drizzle of celestial driftwood, each piece a tiny, frozen story of a system's violent birth and the material it cast away into the infinite night. All these strange worlds and cosmic architectures lead us to a single, profound question. Are we alone in the universe? The search for life is the ultimate mystery, a puzzle that connects every bizarre planet and chaotic orbit we have explored. The existence of hot Jupiters suggests violent histories that could sterilize inner systems. Tidally locked eyeball planets present a fragile, narrow path for life. The prevalence of rogue planets hints at vast, dark oceans where life might cling to internal heat, completely independent of starlight. Each discovery adds a new variable to the cosmic equation of habitability. The sheer number of planets is staggering, suggesting opportunity everywhere, but the gauntlet of challenges, from stellar flares to the slow stripping of atmospheres, implies that a stable, long-lived cradle for life might be incredibly rare. Our own solar system, with its protective Jupiter, its magnetic field, and its fortuitously circular orbit, might be a greater cosmic anomaly than we ever suspected. The answer, however, may be within our grasp. A new era of astronomy is dawning, one that will peer directly into the air of distant worlds. The James Webb Space Telescope is already analyzing the chemical composition of exoplanet atmospheres, looking for the subtle fingerprints of water vapor, carbon dioxide, and other gases. But the next generation of observatories will take this search to its logical conclusion. Missions like the planned Habitable Worlds Observatory are designed to directly image Earth-like planets around Sun-like stars. They will not just detect atmospheres, they will scrutinize them for biosignatures, combinations of gases that are difficult to explain without biology. The simultaneous presence of large amounts of oxygen and methane in an atmosphere would be a powerful signal, as these gases react quickly and would vanish without constant replenishment. Finding such an unstable, biological cocktail around a rocky world in the habitable zone would change everything. It would mean that the universe is not just a beautiful, chaotic, and violent place. It is also a living one. We stand on the threshold of this discovery, armed with the knowledge of 24 other mysteries that shape the cosmos. Every strange orbit and evaporating world has taught us what to look for and what to avoid. The great silence may not be a silence at all, but a conversation we are only just learning how to hear. The answers are out there, hiding in the light of a distant star, waiting for the right moment to reveal themselves. This journey through 25 cosmic puzzles has revealed a universe far wilder and more wonderful than we ever supposed. Each mystery, from the tilted orbits of rogue giants to the silent whispers of evaporating worlds, is a vital piece in the grand puzzle of planetary science. These are not just curiosities from distant stars, they are the keys to understanding our own home. Every chaotic system we find forces us to re-examine the calm of our solar system, asking why our neighborhood is so quiet, so orderly, and so hospitable to life. The study of exoplanets is a science still in its infancy, a field where every new telescope observation can overturn a decade of assumptions. The biggest discoveries are not behind us. They are waiting in the data streams of future missions in the light of stars we have not yet even named. This is an invitation to you to stay curious. The next time you look up at the night sky, remember that you are not just seeing points of light. You are looking at a trillion possibilities, a cosmic ocean of worlds, each with its own story of fire, ice, and mystery. The greatest secrets of the cosmos are still hidden, waiting for the next generation of explorers to bring them into the light. We want to know which of these 25 mysteries captured your imagination the most. Was it the potential for life on a rogue planet, or the violent history of a hot Jupiter? Share your thoughts in the comments below, and if you are ready for more journeys to the edge of our understanding, subscribe and join us as we continue to unravel the universe one mystery at a